So now we will talk about second part of this chapter. We will be talking about self-induction phenomena and RL circuits. In Faraday's experiment, there was two circuits. One circuit which have a battery and the current flowing in the circuit through a loop. The loop will generate a magnetic field, and the first magnetic field will pass through the second loop, and if this magnetic field or magnetic flux changes with time, this will induce an EMF in the second circuit. In this experiment here, we will have just one circuit. So basically we have a solenoid that replaces our loop. So we have n certain number of loop or turn, and this solenoid is connected to a battery. And the arrow shows the direction of the current on the solenoid. When the current flows through solenoid, it will generate a magnetic field in this direction toward the left. How I know this? You put your hand in direction of current, you see that your thumb is pointing to the left. So that's the direction of the magnetic field. Another way how to do it, you put your thumb in direction of current and you see that your hand are pointing toward the left. So that's the direction of P. Steady current will generate a steady magnetic field. Now, let's do something like Faraday's did. I'll try to change the flux of this field, changing the current. I change the value of the current. So, for example, I increase the current. When you increase the current, you increase the value of B. So you increase the magnetic flux passing through the same solenoid. So basically, what we will have? We have the flux of B increasing, according to Faraday's law. There should be an EMF induced in the solenoid, in the same solenoid. The direction of the EMF is such as it opposes the increase of the flux, magnetic flux. So basically, where is the direction of the induced magnetic field? Well, if B is to the left, so B is increasing, so B induced is to the right. So it means that the current should be in opposite direction. We deduce that the EMF is to the right. The induced EMF in the same solenoid is to the right. We call it EL. Let's take the opposite situation. Let's have a current decreasing. It means that the flux of B is decreasing. And where is the direction of the B induced? That's the same direction of the initial B. If you revise well your Lenz's law, you will understand that. Because actually what is happening? B is decreasing, so there is less number of magnetic field lines. The EMF, it opposes that. It opposes this decrease. So B induced should be in the same direction, trying to increase the flux. The flux is decreasing, so the EMF tries to increase the flux. So B induced should be in the same direction of the initial B, and the current will be in the same direction too. The induced current. Sorry, here, that's the induced current. The EMF will be in this direction. So we can draw the same thing. The EMF is like that. That's EL. To summarize this, we have it in circuit notation. So that's how we draw a solenoid in circuit. Okay, we'll come back to that in the next slide. And we have the direction of the EMF. It opposes the change of the flux. So according to Faraday's law, the EMF is equal to minus N d phi B over dt. Thus we will write it also to minus L di over dt, because what is changing here actually is a current. So there is a rate of change of current. So the EMF should be proportional somehow to the rate of change of the current. And the coefficient of proportionality, we call it L. So let's see what is this value of L. I can write this like that, minus d over dt of what? Of n phi b. And we will see that L also is a constant, so I can put it inside derivative 2, so I get something like that. From this you can deduce that n times phi b, flux of B, equal to L times the current, equal to product of the number of turn or number of loop by the flux of magnetic field divided by the current passing through the inductor, the solenoid. Phenomena is called self-induction. So let's come back now to the notion of inductor inductance. Basically what we call an inductor, that's any device that has loops. So one loop is an inductor, a coil with n loop is an inductor, a solenoid is an inductor, a toroid is an inductor. That's how we draw inductor in circuit. The inductor, it has an inductance. Find it as the number of turn times the flux of magnetic field passing through the inductor divided by the current circulating through the inductor. The unit of the inductor, that's the unit of flux, which is a Weber, we can call it also Tesla meter square per ampere. This quantity, we call it Henry. So 1 Henry, 1 H, is equal to 1 Tesla meter square per ampere. Name comes from the scientist Joseph Henry. So let's calculate now inductance, parameter of proportionality between the induced EMF and the rate of change of the current. Start from this formula. So what is the magnetic field through a solenoid? That's mu 0 I n, being the number of turn per unit of length. And what is the magnetic flux? Well, that's this times the cross-sectional area. The cross-sectional area, although it's circular, I will just assume it to be A. So mu 0 I n times the cross-sectional area. So in order to get the inductance, what I need to do, I need to multiply it by number of turns. So n mu 0, the same current, I n times A over I. But what is n? N actually is the number of turn per unit of length. So in number of turn per length of a solenoid, if you put it here, you will get mu 0 I n square A L over I, and I will cancel out. So it's just mu 0 n square A times L. Mu 0, that's physical constant, that's permeability. N square, that's number of turn per unit of length. So that depends on the design of your inductor, of your solenoid. The area, that's cross-sectional area, and L, that's the length of a solenoid. So basically, similar to capacitance, the inductance depends on what? On geometry, on design of your inductor. Generally, we like to write the inductance per unit of length, and this is equal to what? Mu 0 n square A. Let's move now to circuits and talk about RL circuits. So what we mean by RL circuits? We have a resistor, a battery, and an inductor. We have this component and we close the switch. What will happen? In absence of inductance, the current is equal to E over R. Now, how we can treat the inductance? Well, the inductance, we can treat it by replacing it with the EMF, with the induced EMF, given by this formula, minus L di over dt, which was open, so the current was 0, and we close it. So what will happen? There is a raise of current. So the current increase. So a raise of current. Okay, so the current increasing. When the current increasing, the EMF it opposes the increase of the current, so it's in this direction. Let's think about this formula, EL equal minus L di over dt. From where it comes? It comes from Faraday's law. But what we said in Faraday's law, what is the meaning of the minus sign? The minus sign, it just comes from Lenz's law. It tells you the direction of the EMF. Once you know the direction of EMF, you don't need the minus sign at all. Basically, you know that the EMF, it should be positive. There is no negative EMF. So, in problems, I ignore the minus sign. It's like it doesn't exist, this minus sign. I need an EMF. I know the formula, basically, L di over dt, but I need the EMF to be positive. We want to close the switch first. And we need to draw a loop and do potential loop rule, like we did in circuit. Alright? And we write the variation of the difference in potential across this loop. So what we can write? E minus Ri, well, I am opposite the direction of the loop, opposite direction of the EMF, so that's minus EL equal 0. What is EL? Is it minus L di over dt? No. It has to be positive. So let's write EL equal L di over dt. Do I need the minus sign? Well, L is positive quantity, as we saw in case of solenoid. Di over dt, well, I have a raise of current. Current is increasing. Di over dt is positive, so that's positive. So that's my EMF. Done. So I can plug this in the equation. I will have E minus Ri minus L di over dt equals 0. That's my differential equation on the current that give me the variation of this current with time. So basically, if you solve it, you will get this formula here. I equal the current equal E over R 1 minus exponential minus t over tau. What is tau? Is L over R. The current it vary in this fashion. So that's quite similar to charging a capacitor. That's the same behavior, that's the same equation, just we replace the charge with the current now. Because we have a differential equation, similar differential equation, on the current. Tau here, that's time constant, same like for capacitive time constant, we have an inductive time constant. Alright? When the time is equal to tau, the current in the circuit is equal to 63% from its final limit. The final limit epsilon, the final value E over R, we get it when we wait a longer time, basically at t equal infinity. We have the current, the voltage, just we derived that. So L di over dt, that's basically the EMF, induced EMF, is equal to what? You will see, if you derive this, you obtain E times exponential minus t over tau. Okay? All right. Right, so the voltage across the inductor is decreasing with time. At t equals 0, the current on the circuit, what is it equal to? 0. What means the current 0? It means that the inductor, I can replace it with what? Those who followed my previous video on complex circuit, they will understand that better. The current is 0, so I can replace the inductor by a broken wire. Let's see at time equal infinity now. At t infinity, when I wait longer time, what we have? We have the voltage across the inductor 0. So with what I can replace my inductor, basically difference in potential here is 0, so these 2 points are at the same potential. It means that the inductor behaves as a wire. These information are not useful when you have a simple RL circuit like that, but when you have a complex RL circuit, that's very, very important. So now we have seen what happens when you increase the current. What will happen when we decrease the current? How we can decrease the current? We can decrease it this way. Let's say in this circuit, I have two switches. So the two switches were open. If I close switch 1, what will happen? The current starts to flow in this outer circuit. So we have a raise of current, we have an increase of current through the inductor that we have solved already. After a certain time, I open the switch. So S1 now is open. I open the switch and I close switch 2. I have already a current flowing in this wire. And now I have RL series circuit without a battery. What will happen? The current will decrease with time. When we had a battery, E minus Ri minus L di over dt equals 0. Now we don't have a battery, so we have just this term. So we have Ri plus L di over dt, I'm just cancelling a minus sign in both sides, is equal to 0. That's simple differential equation that is solved like that. The solution of this differential equation is given by this. I equal E over R exponential minus T over tau. Or more exactly, I naught exponential minus T over tau. That's the solution of this equation, and tau is L over R, is the capacitive time constant when we have a decay of the current. So here we have a decay of current. Why here we have E over R and here we have I naught? Well, this depends on the first experiment. On the first experiment, when you connect this circuit, this RL circuit to a battery, it depends when you stop that experiment. If you wait longer enough time, the current flowing in the circuit will be equal to E over R. If you wait just less than that, you have a certain current, which is I naught, okay, which is different than E over R. So if you start with I naught, what is the current? What is decay of the current? That's I naught exponential minus T over tau. Okay, that's all what I want to say in this chapter. Thank you for watching. See you in my next video.